Okay, greetings. Let's get started with today's class. So we were looking at engine emissions. So broadly, emissions from IC engines, can be classified as what are called exhaust emissions that come from the tailpipe, which include all these gases: unburnt hydrocarbons, oxides of carbon, oxides of nitrogen, oxides of sulfur, and also emissions in the form of particulate matters. So in addition to exhaust emissions, there are what are called as non-exhaust emissions, which are mainly unburnt hydrocarbons that come into the atmosphere due to evaporative losses in the fuel tank and other elements like carburetors. And you can also have what is called as crankcase blowby, where some fuel escapes through the crevices in the piston cylinder assembly, okay, between the piston rings, oil rings and the cylinder surface, okay. So that constitutes those constitute non-exhaust emissions. So we are going to look at both categories of emissions, and we are going to look at each component of these emissions in today's class. And we will also look at what happens in various types of engines like 4-stroke SI and CI engines and also in 2-stroke engines. So if we look at the ideal combustion process in any internal combustion engine, we provide fuel which is a hydrocarbon. Many times sulfur is present in the fuel, okay, and we take in air, predominantly a mixture of nitrogen and oxygen. And when we combust them and when we burn them together in the combustion chamber, chemical reactions occur, and in the ideal scenario we should get these as the byproducts of combustion. That is, the exhaust should contain carbon dioxide, water vapor, nitrogen as it is as N2, any excess oxygen as O2, and maybe some oxides of sulfur. Okay, so that is as close to the ideal process that we can expect. So in other words, all the hydrogen and carbon in the fuel must be completely oxidized, so that we also avoid other exhaust emissions and also ensure that we are able to retrieve the maximum possible chemical energy from the fuel and convert it into thermal energy. So that is the ideal scenario. In the real combustion process, more often than not, we will get these gases CO2, H2O, N2O2 and oxides of sulfur, but in addition we would also get unburnt hydrocarbons. UHC stands for unburnt hydrocarbons, okay. We will get carbon monoxide, CO, carbon in the form of particulate matter, what is called as soot. We may get NO and NO2. NO and NO2 are typically combined and represented as NOx. Some people will refer to as NOx, okay, as a term, okay. So we are going to get all these additional gases as byproducts of the combustion process in the exhaust, and these have severe implications on the environment. And in addition to that, we are also going to see what impact they have on the engine per se, right. So that is something which we are going to look at. So this is the actual scenario. So let us start looking at what happens in each type of engine, and then we will also discuss each component of this emissions, right. So first, starting with emission from SI engines. Typically what happens is that in spark ignition engines and also in both 2-stroke and 4-stroke, what is going to happen is that a rich fuel air mixture would not have, would have what to say, Hc and Co, since there is insufficient oxygen for complete oxidation. Okay. So, the oxidation process is not complete, right. So, if the oxidation process is not complete, like essentially we are going to have this unburnt hydrocarbons and oxidation process, unburnt hydrocarbons and carbon monoxide present in the engine exhaust. Okay. And when would this NOx emissions also come into play? In fact, the oxidation of this one, like so, let me call it as oxidation, right. So, the NOx gets formed if, and the oxidation of NOx happens or nitrogen happens, like at high temperature. At high temperatures in these cylinders, N2 will result with O2 to form this NO and NO2. So, whenever we have this condition of high temperatures in the cylinder, we are going to have NOx formation. And when would the cylinder temperature be the highest? When the fuel air mixture is close to the stoichiometric mixture. When we have fuel air mixture to be at the close to the stoichiometric ratio, our what to say, combustion process is going to be pretty efficient as far as the conversion of chemical energy to thermal energy is concerned, and the cylinder temperatures would peak. Okay. So, NOx emissions depend on the combustion temperature and hence are the highest at near stoichiometric conditions. Okay, that is when, okay. So, that is when the NOx emissions become the highest. Of course, typically maximum NOx emission or happens at a slightly lean condition. Okay. So, if you compare it, it happens at a slightly lean condition because at this condition the cylinder temperature is sufficiently high and there is enough excess oxygen also. See, we need oxygen to react with nitrogen, right. So, if you have exactly stoichiometric, right, so there is only enough oxygen to react with the hydrocarbon and oxidize them, right. So, there will not be any oxygen left if the fuel air ratio is exactly stoichiometric. So, slightly lean mixture. So, there will be enough heat energy that is released to ensure that the cylinder temperatures are sufficiently high, and also there is enough oxygen to react with nitrogen. So, if we take it consider a typical what to say distribution of these gases, you know, like in a spark ignition engine, you know, like it looks something like this. So, yeah, of course this should be stoichiometric. Okay. So, if we plot the fuel air ratio, right. So, and essentially look at how the emissions get affected in spark ignition engines. So, let us consider the equivalence ratio, right. So, as we know, this side is lean, to the right of the what to say the vertical line at 1, it is going to be a rich mixture, right. Unsurprisingly, in a rich mixture, the hydrocarbon content and the carbon monoxide content increase, right. So, hydrocarbon and carbon monoxide okay, sorry, right. So, Hc and CO content increase, okay, in a rich mixture, because obviously we are going to have more unburned fuel, right. And we can see that NOx emission, which is represented by these curves, you know, like become the maximum at slightly lean mixtures, okay, near stoichiometric conditions, and that is where they become the maximum. Okay. So, this is typically in emissions in what to say SI engines. In addition, the question is what happens in 2-stroke SI engines. Okay. So, this is a general trend in SI engines, but what do you think will happen in 2-stroke SI engines when compared to the 4-stroke SI engine? In 2-stroke SI engines, we can immediately see that the process of scavenging would result in more unburned fuel escaping with the exhaust. So, if we recall how 2-stroke engines operate, we can recall that the exhaust port is open during the downstroke, and during the same phase fresh fuel air mixture is going to come from the crankcase through the transfer port to the combustion chamber. So, there is a good chance of not only exhaust gas dilution of fresh charge and also fresh charge escaping into the exhaust, right, port. So, due to these reasons, the chances of unburned hydrocarbon being more increase in a 2-stroke engine. Okay. So, in a 2-stroke engine, the process of scavenging results in unburned fuel escaping with the exhaust. Okay. So, that is what happens in a 2-stroke engine. And not only that, please recall that in a 2-stroke engine we add lubricant along with the fuel, and the lubricating oil has a different chemical composition when compared with the fuel, and that is also going to go into the cylinder, undergo combustion to varying extents, and whatever is left behind is going to be exhausted through the exhaust port. Okay. So, we have to look at that aspect also. The lubricant oil or the lubricant fluid that has a higher molecular weight okay, is also going to undergo incomplete combustion in the combustion chamber that further adds to the hydrocarbon emissions. Okay, so that is what these are two important factors that we need to keep in mind when we look at emissions in two-stroke engines. Okay, so in addition to whatever we have already seen about SI engines, right, two-stroke SI engines. Okay. So now we will come to CA engines shortly, but before that let us look at each component one by one, right. So and then like that will also give us an idea as to which component is going to be important in what type of engines. Okay. So let us first look at the first component that we are going to look at is hydrocarbon. Unburnt hydrocarbons. Okay. So let us abbreviate it Hc. Okay. So what, as we already know, hydrocarbons we can have two aspects. So this is, we can have unburnt fuel compounds as they are, right, in the exhaust, but also like partially reacted compounds, right, particularly when we have high molecular mass hydrocarbons, they can be oxidized partially, right, they can go to a different chemical structure and still be released along with the exhaust. Okay. So partially reacted compounds, they form when large fuel molecules break up, okay, due to the heat energy during the combustion process, and this is what is called as thermal cracking. Okay. So thermal cracking is this phenomena where these larger molecules break down into smaller hydrocarbon molecules, and these are also released. And what are some limitations with hydrocarbons? Obviously they act as irritants for us and odorants. Okay. Some are carcinogenic too, right, and hydrocarbons react with atmospheric gases to form photochemical smog, which is once again very harmful, right. Smog is harmful for all living things. Okay. So essentially higher hydrocarbon content can be present in rich mixtures, because why? Because obviously they have less oxygen, right, to completely oxidize the fuel particles, right. And unburnt hydrocarbons are also present in too lean a mixture. Why? Because they may not have enough fuel to even like sustain the combustion process, right. So either too lean, as we can observe, too lean a mixture would also increase the hydrocarbon content, right, because we essentially cannot sustain the combustion process. Okay. So that's a reason for what to say, increasing hydrocarbon content when we go to very lean mixtures. Okay. So neither is advisable, too rich or too lean, right, from a hydrocarbons emission perspective. Now let us look at causes for Hc emission. Let me quickly run through them. In SI engines, you will see that even in CA engines, you know, like many of these causes are going to come in, but first let us look at what happens in spark ignition engines and what factors are result in significant hydrocarbon emissions. Okay. So the first one is due to incomplete combustion obviously, right. So, the combustion process is not incomplete, sorry, it is not complete, okay, and there are multiple reasons for this. One is due to improper mixing of fuel and air, because if the fuel and air do not mix properly to form a homogeneous mixture, we are going to have incomplete combustion, right. So, that is one reason. Second factor is what is called as flame quenching. So, what is meant by flame quenching? The flame gets put out before it can burn all the fuel, like unburnt fuel, right. So, why does flame quenching happen? So, when the flame gets closer to the wall, it can get quenched, right. When the flame front hits a wall, it can get quenched, okay. So, that is one reason. Flames also get quenched during expansion of burnt gases that result in reduced temperature and pressure, right. So, when the combusted gases expand, right. So, the pressure and temperature are going to decrease in the combustion chamber, and due to that a flame may get quenched, okay, increased temperature, okay. And another potential reason is contamination with exhaust gases, right. So, because typically there may be exhaust gases that may mix with the fresh charge, right. A part of exhaust gases may also remain in the cylinder from the previous cycle, and where the concentration of these exhaust gases is high, the flame may get quenched, right, because it may not have enough fresh oxygen, right, to carry out the combustion process, right. The fuel air mixture may not be combustible, okay. So, incomplete combustion predominantly happens due to these reasons, and that increases the level of hydrocarbons in the exhaust, okay. So, what can be another reason? Okay, there are multiple reasons. So, essentially fuel trapped in piston ring, compression, oil ring, crevices. So, what happens, right, as we already seen, a compression ring or a piston ring provides a seal, right, and an oil ring is also installed on the piston periphery. So, now although like these are carefully manufactured and assembled, still we are going to have small crevices, right, and the fuel air mixture is going to be forced through these crevices, and during the compression stroke, okay. So, the fuel air mixture may be forced into these crevices, okay. So, at high pressures, right. So, now when expansion happens, what is going to happen? The pressure in the cylinder is going to drop down, then there is a pressure difference in the opposite direction, is it not? Okay. So, this unburnt fuel air mixture which are essentially captured in the crevices may come out, because now the pressure is lower in the cylinder, right. So, during expansion stroke, this may come back into the cylinder, okay, and this increases the unburned hydrocarbon. This can potentially increase. So, this process is what is called as reverse blow by, okay. So, if you encounter this term, what is reverse blow by? Like essentially we looked at crankcase blow by, right, unburned hydrocarbons blow past the rings and then into the crankcase and then escape. So this is like a part of it, like comes in the reverse direction. First they are forced into the crevices, but a part of it comes back in, right. So that is why it is called as reverse blow by, okay. So that is one reason for hydrocarbon emission, okay. So let us go ahead. So another reason for unburned hydrocarbons is leakage past the exhaust wall. See, even the exhaust wall can have crevices, right. So fuel air mixture is forced into the crevices around the exhaust wall components, exhaust wall seats and so on, right. So around the exhaust wall, okay. So now when the exhaust wall opens, this will escape, okay, through it into the exhaust manifold, right. So that is why essentially we have leakage past the exhaust wall, right. So this fuel air mixture, which is stored in the crevices, escapes into the exhaust manifold when the exhaust wall is open. Okay. So EV in this context means exhaust wall, okay, right. So that is another reason. So let us look at more reasons. So in any engine there is a significant amount of valve overlap, right. So because when the if you recall the 4 strokes in a 4-stroke engine, right, there is always some overlap between the exhaust valve closing and the inlet valve opening, and that is going to result in two things, like some exhaust valve polluting the fresh charge and also what is called as exhaust gas dilution, and some what to say fuel air mixture escaping also, right, both can happen, right. So that is what to say, that happens, it can be minimized with careful design, but there may be some component, right. So that is why it is called as valve overlap. And when will this be more significant?
Higher RPM.
At lower RPM. If you recall, at lower RPM there will be more time available for each stroke, right. So then as far as time interval is concerned, each stroke will have more time, and consequently the overlap may occur over a larger time interval, and that will promote this fresh fuel air mixture escaping into the exhaust what to say manifold, right. So when the inlet valve and exhaust valve are simultaneously open, a part of the fresh fuel air mixture may flow directly into the exhaust, okay. That is due to valve overlap, okay. So this is more severe at idling and low speeds due to longer time of valve overlap, right. So that is another reason. So another reason due to higher what to say behind hydrocarbon emissions in the exhaust is due to absorption by valve deposits and lubrication oil. So see, anyway on the cylinder, like we are going to have also other chemicals, other components, other compounds coming in with the fuel, right. There are going to be other reactions, right, and we will have valve deposits forming on the cylinder walls, and even we will have these lubrication oil deposits. What will happen is that typically these will absorb the fuel vapor okay, during compression, combustion and so on, and then later release them. Okay. And as the engine keeps on aging, right, as the age of the engine keeps on increasing, what may also happen is that the lubricating oil film may become thick with age, and a part of it may get peeled off, right, with continuing operation, and that will also come through the exhaust, right. So, all those will contribute to the hydrocarbon emissions. So, all these factors contribute to hydrocarbon emissions in engine exhaust.